After a rain shower, the sky sometimes switches on a giant curved ribbon of color. Qubit calls it weather showing off. But a rainbow is not a painted bridge, and there is no pot of gold attached. It is sunlight, water droplets, geometry, and your eyes working together in a very precise way. Sunlight looks white, but it contains a continuous spread of visible wavelengths. Our eyes interpret different parts of that spread as different colors, from red through orange, yellow, green, blue, and violet. A glass prism can separate them. Qubit tries sorting sunlight into jars, but the lids keep glowing. Now imagine millions of nearly spherical water droplets floating in the air ahead of you, while the sun is behind you. Each droplet is a tiny optical laboratory. The droplets are not painted different colors. Almost every useful drop receives the same broad mixture of sunlight and redirects different wavelengths by slightly different amounts. When sunlight enters a droplet, it passes from air into water and slows down. That change in speed bends the ray. This is refraction. Unless the ray enters straight through the center, its path turns at the curved surface. Qubit demonstrates by marching straight, then slipping sideways into a paddling pool. Water bends shorter visible wavelengths slightly more than longer ones. This wavelength-dependent bending is called dispersion. Violet light changes direction more than red light, with all the other visible colors spread continuously between them. The separation begins as light enters, although one tiny droplet alone does not look like a striped sweet. The refracted light travels across the droplet and reaches the back surface. Much of it leaves, but some reflects back inside, like light bouncing from a curved mirror. The bright primary rainbow mostly comes from rays that make one internal reflection. Qubit gives the droplet a scorecard. The reflected ray crosses the water again and exits through the front side. It refracts a second time as it speeds up from water into air. Entry refraction, one internal reflection, and exit refraction together send the separated colors back towards an observer at particular angles. That three-step journey is the primary rainbow recipe. For the easiest rainbow view, keep the sun behind you and rain or spray in front of you. The rainbow is centered on the anti-solar point, the direction exactly opposite the sun. You cannot usually see that point because it may lie below the horizon. Qubit turns his back to the sun and finally faces the shore. In a primary rainbow, red reaches your eyes from droplets roughly 42 degrees away from the anti-solar direction, while violet arrives at a slightly smaller angle. That puts red on the outer edge and violet on the inner edge. Other wavelengths fill the space between. Each colored ray usually comes from a different droplet. The bow appears where countless correctly placed droplets send light to your eyes. Move sideways, and a new set of droplets takes over. There is no glowing arch sitting at one fixed distance, so you cannot walk underneath it. Qubit attempts to chase the end. The rainbow calmly updates its location and wins. A rainbow is actually a circle around the anti-solar point. From the ground, the horizon usually blocks the lower part, leaving an arc. From an aircraft, a high mountain, or above a waterfall with droplets below, you may see much more, even a complete circle. Qubit wants a circular rainbow as a cosmic hula hoop. Because the geometry is tied to the observer's eyes, two people standing apart do not receive rainbow light from exactly the same droplets. They can admire what looks like the same bow, but each person has their own optical version. Even your left and right eyes sample slightly different droplet paths. Rainbows are surprisingly personal. Sometimes a fainter secondary rainbow appears outside the primary. Its important rays reflect twice inside each droplet before leaving. Extra reflection loses more light, so the secondary is dimmer. Two internal bounces also reverse the color order. Violet lies on the outer side, and red lies on the inner side. Look between a strong primary and secondary rainbow and the sky may seem darker. This region is called Alexander's band. It is not a dark cloud stripe. The main ray paths that brighten the two bows send less light towards your eyes from those in-between angles, making the contrast visible. Qubit lowers the imaginary dimmer switch. Textbooks often name 7 rainbow colors, but nature does not draw hard borders between 7 paint strips. The spectrum changes smoothly across many wavelengths, and human color vision groups that continuous spread into familiar names. Brightness, background, droplet size, haze, and eyesight can change which colors appear strongest or easiest to separate. You do not need a rainstorm to make rainbow physics. Sunlit spray from a waterfall, fountain, hose, or mist bottle can form a small bow when the angles line up. Prisms also reveal dispersion, although their shape redirects light differently from spherical drops. Qubit's garden sprayer becomes a pocket-sized rainbow machine. The sun should be fairly low for a ground-level bow to rise clearly above the horizon. When the sun climbs higher, the rainbow's center moves farther below it. Search safely with the sun behind you. Never stare at the sun, even through clouds, cameras, binoculars, or Qubit's very shiny magnifying gadget. So here is the full rainbow recap. Broad-spectrum sunlight enters water, refracts and disperses, reflects inside, refracts out, and reaches your eyes only from droplets at the right angles. One mean reflection makes the primary, two can make the reversed secondary, geometry makes the arc or circle. Qubit packs an umbrella and a protractor.